Hello, everyone. My name is Antonio Castellanos, and I'm a PhD student at the Technion in Israel. Thank you so much for choosing us as finalists in this year's Palms Applied Research Challenge. I will talk today about the co-production of service and some stochastic models that we're proposing to model service times in contact centers. This is a joint work with my advisor, Khalid Yomtov, Andrew Daw from USC, Jamal Pander from Cornell, and Lior Grudlinger from LivePerson Inc. LivePerson is one of the leading platform developers for contact centers. Throughout this project, we collaborated with LivePerson. They provided us with data and insights. Additionally, Lior Grudlinger, the former principal data science and machine learning engineer, collaborated with us, the academic team. So I want to start by talking about the indigeneity of service times. In this review paper by Delsey et al., they state that service durations are not exogenous, but are in fact dependent of the state of the system in some form. Specifically, in contact centers, service durations are affected by concurrency, how many customers the agent is serving at once. That, of course, affects performance. Then we have the amount of information and even the level of emotion exchanged within a service interaction. And finally, in particular, the roles within the service, the agent and the customer. That gets us to the very title of our paper, the co-production of service. What I'm referring to here is even going back to some of the original writings on the service economy. This quote from 1968 that was recognizing that the achievements and the productivities within services not only depend on the agents, but also on the customer. Both parties bring something to the table. So I'm going to be often contrasting co-production, where the agent and the customer fully rely on one another, with self-production, where both the customer and agent operate largely independently. In contact centers, our particular context, communication is text-based. These contact centers are becoming quite popular, mainly because they're so flexible. That flexibility shows up on the customer side. You can be messaging with an agent and go about with your day, but it's also flexible for the agents, since they can be working with multiple customers at once, the concurrency that I referred to in the beginning. This also means that they are very interesting. There's a lot of very interesting work happening in that space. Another reason that contact centers are so nice to be studied is that they have very rich data. So what I'm showing you here on the left is a snapshot from our data set for one agent for the course of 2 hours. We can see the 7 customers that he's interacting with over the course of time. The squares represent when the agent sent a message, and the circles when the customer did. So we can see the burstiness of the communication in these clusters of messages. And we can also notice long lags of inactivity. That leads to the disparity that you see in the histogram on the right side. We notice the difference between the assigned number of conversations to agents and the number of active conversations. These differences suggest that there's actually some operational disparity on how an agent workload should be measured. That's going to lead us into our modeling philosophy. We're going to zoom in on a service conversation. We're going to model the conversation as a dynamic stochastic process. So in particular, I want the history of the communication to shape the future of the communication moving forward. So that type of modeling structure from a stochastic modeling perspective is quite similar to the Hawk's self-exciting point process. This process is a stochastic intensity point process in which the current arrival rate, in our case of messages, is dictated by the history of what occurs so far. So what I mean by this is this arrival rate lambda t is given by an integral, or you can think about it as a sum over the process history so far, that point process nt. And that's what you see in the example sample path at the top of the slide. When an arrival occurs, it increases the likelihood of an arrival occurring soon. This function g will regulate that excitement so it doesn't just explode. That's how you get the clusters of activity like we saw in the data. Excitement driving the conversations up and some regulation leading to some pauses in between. So what I'm going to do now is introduce 3 successive models. They're going to encapsulate one another. So I'll walk from the ground up, and I'll start here with the univariate Hawkes process, the UHP. Again, lambda t and nt are a point process, my correspondence rate, and the number of messages. I have an exponential decay kernel, so I have alpha, which is the jump in the correspondence rate upon each message, and beta as the decay rate between messages. So moving now to the bivariate, I'm going to have a customer message process and an agent message process that influence one another via these co-production rates. And I'm also going to include the self-production response rates, customer to customer and agent to agent. So for our final model, I'm going to include an endogenous dependence on the system. I'm going to call this model the system bivariate Hawkes process. So the CSBHP. So our jump sizes are now going to be a linear combination of the sentiment expressed in every message and the amount of information in every message. Now, I also want to reflect the fact that the agent is serving multiple customers and how it affects his performance. That's what I'm doing, dividing by the concurrency KT. So someone might say that these correspondence rates appears if we're counting presumably until infinity. So to show that we won't, we actually have a stability condition for the CSBHP. If this condition that I'm showing at the top of the slide holds, I know almost surely that I will have a finite number of messages in a conversation. The only other thing I want to point out is a way that we project the upcoming number of messages with the Hawkes models, which will be relevant for practice. What I'm saying here is, I've seen the conversation up to time t0. I can, through a linear algebra calculation, project the number of messages that are going to occur in an upcoming time interval. Now, I want to see how actually these models can be applied to practice. The first step we tackle is checking their fit to data. So we have a large data set that was provided by LivePerson. How do these models actually do here? What I'm showing you here is these 2 figures where we see the difference of the data CDF and the CDF of the simulated models. So on the left, we're talking about the whole duration of the conversation, and on the right, the gap time, the time between messages. If we had a perfect match, we exactly replicated the data, we would be right along that dash x-axis line at 0. These are visually informative, but they also relate to very common distances of distribution, the Kolmogorov-Smirnov and the Wasserstein. So what we see here is that the BHP has a very good fit on both, but then the CSBHP provides the best performance on the gaps. When we dive into the parameters of our models, we can get very interesting insights. We show with them in the paper the importance of considering the history dependence of the conversation and the central role of the customer, since he is the one that drives the conversation in the long run. Now, I'm going to move to what the models can be used for. Routing seems to be a very natural situation for these models. So I'm going to pull this policy, that is the one that is used in the contact center, the lightest load policy. If there are agents with available capacity, we send a new customer to the agent with the least assigned customer. If multiple agents have the same number of assigned customers, we break ties randomly. So this policy is going to be our baseline. We're also going to do a very modest modification. Instead of breaking ties randomly, we're going to choose the agent with the least number of messages in an upcoming time window based on the Hawkes projection that I mentioned before. To evaluate these policies, we're going to run an entirely data-driven simulation. So we're pulling the customer arrival times, the response times, staffing level, and maximum concurrency directly from our data. And the only thing that we're controlling here are the policies. So what we see here in these figures is the mean improvement relative to the baseline lightest load policy. And as you can see, we're getting a significant improvement. 10 to 20% in the outer weight, meaning weight before service, and around 4 to 6% improvement in the inner weight, so the weight in service, while customers wait for their assigned agent to respond. And also we get an improvement in the probability of waiting. In general, the CVHP in the green line is outperforming the BHP in the purple line, which is outperforming the UHP in the red line. And we're not just reducing the mean, we're actually reducing variability in the system by reducing the standard deviations by 3 to 6%. In the next part, we will hear from Lior, our industry partner, on how our models are relevant to practice, since in the past, the company has used and patented a more basic prediction-based routing.
I am Dr. Lior Grundlenker. I worked in LivePerson. During the years of this research, we had a very fruitful collaboration with the academic team. And I will tell you a little bit about the practical implications of this work. LivePerson was actually a pioneer in going from the fixed concurrency to looking at each conversation separately and trying to say something about the required workload from the agent. And we had a simplified version of the current work, which was not based on a Hawks process, which is as flexible as described here. It was slightly different method, but we immediately found out that this was a deal breaker for many of our customers. We started with a very simple predictor, with even a rule-based predictor about how much workload each conversation we expect to assign to each agent. We could immediately improve the routing algorithm, and then the efficiency of the agents increased without hurting the wait time KPI of the customers, and many more of LivePerson's customers, which are enterprises with large contact centers, could start using messaging at a scale. So this was kind of the first step. So this is maybe the time to introduce why the Hawks process could be so useful here, because as it is shown in the article, the Hawks process prediction can reduce the amount of unexplained variance in predicting the required number of messages or the message rate of the agent in the near future. And this immediately translates into a better ability for us to improve the routing. That as the predicted load is more similar to the actual load on the agent, the workload on the agent, then the performance of the routing algorithm improves. Very useful for our staffing and also for getting the alphas and betas themselves are useful, could be useful for us as quantifications of the influence between consumer and agents, which could be used later on because we would like to teach our agents or the agents of our customers how to better set the tempo of the conversation. And when we have a quantitative marker of the influence the agent has on the customer and the customer is on the agent, then we have a way, so we hope, to develop training methods for the agents so they can set the kind of correct tempo so that the customer on one hand doesn't vanish from the conversation and on the other hand doesn't respond too quickly to stress the agent. So this is again a useful property of the Hawks process model that we can hope can be used in the future. And still, as a closing remark, human behavior is very hard to predict, as you all know. There's still a huge amount of unexplained variance, and everything we can do to help reduce our prediction error here would be useful. We are looking into using text in other ways. We are looking at all kinds of other indicators that could hopefully combine with the Hawkes process and other methods in order to improve the accuracy of our prediction of agent workload.
Thank you very much for listening to my talk. The paper is available in the website of my advisor. Thank you.